So this video will show you how to solve for the final velocity of two different objects when they undergo an elastic collision. So here we have two gliders on an air track. The air track guarantees that the collision, or the system I should say, is an isolated system because there's no external force of friction when you use an air track. And momentum is only conserved if collisions are both closed and isolated. Anyway, we know that momentum is conserved, and that can be stated as an equation in the form m1u1 plus m2u2 equals m1v1 plus m2v2. And that gets us somewhere, but it can't solve the whole problem because there are two unknowns in this equation, so we need a second equation. The second equation is a statement of the law of conservation of mechanical energy, 1/2 m1u1 squared plus 1/2 m2u2 squared is 1/2 m1v1 squared plus 1/2 m2v2 squared. So we're just going to do a little bit of arithmetic and algebra to try to combine these two equations into one single expression. So let's continue with our statement of the law of conservation of momentum. So we're going to skip over this idea of conservation of energy for now and find a way to rearrange this equation. So we'll get all the ones on one side of the equation, all the twos on the other. And we have m1 times the quantity u1 minus v1 equals m2 times the quantity v2 minus u2. Okay, not bad. Let's do this. Let's try to rearrange the equation that states how kinetic energy is conserved. I can multiply through both sides of the equation by 2 to cancel all the 1/2s, and then I'll do the same thing. I'll try to get all the 1s on one side of the equation and all the 2s on the other. So we get m1 times u1 squared minus v1 squared equals m2 times v2 squared minus u2 squared. Let's see. I think I can take that a step further and say this is the same thing as m1 times u1 minus v1 times u1 plus v1, see where I'm going with this, equals m2 times v2 minus u2 times v2 plus u2. All right. Now we have two equations that look very similar. This equation resulted from the law of conservation of momentum. The second equation, stated in orange, results from an expression of the law of conservation of kinetic energy. The two have to hold true, and if I added the two equations to each other, that would be a valid equation if I subtracted one from the other. In this case, I'm going to divide one equation by the other. I'm going to divide the equation in orange by the equation stated in green. When I do that, m1 cancels m1, m2 cancels m2, and then even this quantity, u1 minus v1 cancels out, v2 minus u2 cancels out, and we're just left with a very simple expression that says the initial speed of object number 1 plus the final speed of object number 1 has to equal the final speed of object number 2 plus the initial speed of object number 2. I think a more meaningful way to look at this is to write it in these terms. u1 minus u2 is equal to v2 minus v1, or better yet, u1 minus u2 equals the negative of v1 minus v2. So I want to introduce the idea of relative velocity. Actually, you've studied this before. Relative velocity is a way of describing how the speed of one object compares to the speed of another. For example, this might be a bit morbid, but if you were driving a vehicle down the freeway at 60 miles per hour and a giant semi, for some reason, is coming at you in the wrong lane, and it's driving at maybe 40 miles per hour in the opposite direction, I think in a way this would feel something like driving your car at what? 100 miles per hour straight into a brick wall, right? So the relative velocity can be found if we call this velocity u1, and I call this velocity u2. I suppose I really mean u2 is negative 40 because it's pointing in the other direction. So the relative velocity is calculated by taking the difference between u1 and u2. In other words, 60 minus negative 40, which gives us 100. So when we take the difference between the two velocities prior to the collision, all we're really stating is what's the relative velocity prior to the collision. If we do v1 minus v2 after the collision, that's a way of stating the final relative velocity. So this is the initial relative velocity, and this would be a way to calculate the final relative velocity. But notice we have negative the final relative velocity. So the way this can be explained, on the air track, the two gliders are traveling toward one another. Glider 1 is moving this way. I think we said it, what was it, 6 meters per second? And then glider 2 is traveling this way at negative 3 meters per second. So the initial relative velocity is equal to 9 meters per second. They're traveling 9 meters per second toward one another. So the only way that the collision can satisfy both conservation of momentum and conservation of kinetic energy is if the relative velocity is conserved in magnitude in the collision. If the relative velocity before the collision is 9 meters per second, then the relative velocity after the collision is 9 meters per second, except it'll change from being toward into away from one another. So, for example, you could have a glider going this way at 6 and this way at negative 3, and then perhaps after the collision, this glider bounces back at 1, and so this glider moves this way at 8. 6 minus negative 3 gives us 9, and negative 1 minus 8 gives us negative 9. The magnitude of the relative velocity stays the same, it just changes direction from toward one another to away from one another. Now, I don't think this is the correct solution, but that's just an illustration. We have to go back to the math to figure out the correct value. In any case, what we have in an elastic collision are two equations. An equation that expresses the law of conservation of momentum, and then instead of having to write out this longer version of a second equation that expresses conservation of kinetic energy, we will use a second equation in this form. u1 minus u2 equals the opposite of v1 minus v2. The relative velocity before the collision is equal and opposite to the relative velocity after the collision. Okay, so we have a second equation to go along with our first equation. m1 u1 plus m2 u2 equals m1 v1 plus m2 v2. So numerically, this was 10 times 6 plus 5 times negative 3 is equal to 10v1 plus 5v2. And we're stuck. One equation for two unknowns, except no, we have a second equation. So 60 minus 15, which gives us 45, has to equal 10v1 plus 5v2. Let's go to the second equation and see what we get. We have a relative velocity of 6 minus negative 3, which comes out to 9, and that has to equal the negative of v1 minus v2, or in other words, it has to equal v2 minus v1. So if 9 equals v2 minus v1, v2 is equal to 9 plus v1, and there it is. We have something we can substitute for one of our two unknown quantities. So we'll go back to our statement of conservation of momentum and reduce it to a one variable expression. 45 equals 10v1 plus 5 times the quantity 9 plus v1. So 45 is equal to 15 v1 plus 45. Well, this was an interesting result. In this case, we had a special condition where 15 v1 equals 0, which means v1 is 0. So the only way in which this collision can satisfy both the conservation of momentum and the conservation of kinetic energy is if the one of the blocks comes to rest and the other one continues moving. And by the way, we saw earlier that v2 is 9 plus v1, so 9 plus 0, of course, gives us 9. So let's just check the results and make sure this all works out. So initially, we had a mass of 10 kilograms traveling at 6 meters per second. It combined with a mass of 5 kilograms traveling at -3 meters per second. 60 minus 15 gives us 45. After the collision, we have a mass of 10 kilograms that's at rest, plus a 5 kilogram object going 9 meters per second, and of course that comes out to 45. So we see that momentum is conserved. The question is, was kinetic energy conserved? So 1/2 times 10 times 6 squared plus 1/2 times 5 times -3 squared is equal to, I believe, 202.5 joules. So let's figure out the final kinetic energy. 1/2 times 10 times 0 squared plus 1/2 times 5 times 9 squared. Does that equal 202.5 as well? Grab your calculator, check it. I think you'll see it does. So the big takeaway here is when it comes to elastic equations or collisions, and only elastic collisions, we can say that relative velocity is conserved in magnitude but opposite in direction. If one block traveling to the right at 50 meters per second collides with and overtakes another block that's traveling to the right at only 30 meters per second, then we would say the initial relative velocity is equal to 20 meters per second. Now we would have to know something about the two masses m1 and m2 to get the exact result, but we know this much. If the first block continued forward at 40 meters per second after the collision, you can be certain what the velocity of the second block would be. I think you can see it would have to go 60 meters per second. And then the relative velocity would still be 20 meters per second, but instead of coming together, the first block would be moving farther and farther away, or the second one would be moving farther and farther away, the first one would be moving to the right as well, but not quite keeping pace, and over time the two of them would actually end up farther apart from each other. So that's the idea. Relative velocity is conserved in magnitude in an elastic collision.